Hi, I'm Eden. I'm the manager of Classiq for Academia, and my background is in physics and electrical engineering with a master's in quantum dynamics. In this video, we are going to discuss the beautiful example of option pricing for the applicability of quantum computers in the financial field. Let's see how you can use Classiq in order to execute a quantum algorithm that tackles this problem. In financial models, we're often interested in calculating the average of a function of a given probability distribution. For example, one might want to estimate the value of an option contract on a future date. Here, we will deal with European vanilla option pricing. This means that a buyer buys the option to buy or sell an asset at a certain price called the strike price on a predetermined date in the future. The value we are interested in is the difference between the strike price and the option price. This is the payoff, which indicates how much it is worth to buy the option. Estimating the payoff to a good precision can make a real difference for financial institutions that offer these options. Therefore, we are interested in estimating the average of this payoff function, where the values of the asset itself are modeled by a log normal distribution. The most popular method to estimate the average payoff is Monte Carlo simulation. Classical Monte Carlo methods, which basically samples many instances of the strike price and calculates the average payoff, generally requires extensive computational resources to provide an accurate estimation. Quantum computers may provide new ways to solve computationally intensive financial problems. The core quantum advantage of several of these applications is the amplitude estimation algorithm. This algorithm enables estimating a desired parameter to the same accuracy, but with a quadratic speedup over classical Monte Carlo methods. Let's get started and see how to estimate these options with Classiq. From the synthesis page of the platform, we choose the option pricing example. On the right, we have the panel where we can configure our problem. First, we choose the log normal distribution for our strike price distribution. The payoff function, which represents the type of the options we are dealing with, is the European call option. The number of qubits is used to discretize the values of the asset. More qubits means better resolution, but for now we will start with 3 qubits. The threshold means the strike price. Now we first need to generate the model in order to apply all our changes, and then we synthesize our model to receive the quantum circuit. This is the circuit we have received. It uses 15 qubits and its depth is 531. Let's understand the circuit itself. We first have the state preparation, which both prepares the log normal distribution and calculates the payoff function. Now let's focus on the quantum phase estimation block, which is the main component within our amplitude estimation circuit. The top qubit here is the phase qubit, which basically stores the results of our algorithm for our final estimation. We see in the middle our control Grover operator, which acts as the unitary for which we estimate the phase. Within the Grover operator, there is a lot going on, including the use of the state preparation we examined before. I encourage you to keep exploring it by yourself with the different levels of hierarchies the Classiq visualization enables. Let's now execute the circuit and see how the results look like. Here we are in the execution page. We will use the IBM Air simulator within the Classiq platform with 2048 shots. And we see that we get, ta-da! These are the final results. As we've seen, we used 1 qubit to store the results, so we get here an histogram of only 1 qubit. By using post-processing techniques, Classiq estimates the average option price from the resulted histogram, and we can see it here. This is very nice indeed. We've been able to design our option pricing model in Classiq to generate a circuit for it, to understand it, and to extract the result from it, all with a simple user interface. Let's see now what happens when we increase our problem size a bit. We now choose 3 qubits for the phase estimation to store the results, and when we generate the model and synthesize, we receive this 10 qubit circuit. We can see the same structure as before, and within the quantum phase estimation, we have now 3 qubits that store the results. When we execute a circuit, we now receive a histogram with 8 possible results. We can see the final result here on the bottom, which is not as before since we changed the parameters of the model at the beginning, but it is more accurate because we used more qubits to store the results. That's it for this video. You are now ready to use Classiq to estimate the most accurate options to sell to your friends or family, and maybe to make a fortune using the most accurate estimators. Who knows? Thank you.
Hello again.